Alright, let's go. Number 10. The quantum eraser. John Archibald Wheeler wasn't trying to break causality. In the 1970s, he was asking a much simpler question. At what point does a photon decide whether to behave like a particle or a wave? The standard model of quantum mechanics predicts that a photon's behavior is fixed by whether a measurement apparatus is set up to detect which path information or interference. Set the trap early, get particle behavior. Leave it open, get a wave pattern. Simple, except in 1999, Yoon-Ho Kim, Yanhua Shi, and colleagues at the University of Maryland, Baltimore County ran the delayed choice quantum eraser and found that the decision to measure or erase which path information could be made after the photon had already been detected. The interference pattern reappeared or vanished retroactively. Kim, Shi, and their co-authors published the result in Physical Review Letters in 1999, and the data held up. Explanation 1. It's just correlation, not real retrocausality, because no usable signal travels backward in time. That explanation survives, technically, but it doesn't tell you why the correlation exists in the first place. Explanation 2. Hidden variables determine the outcome all along, ruled out by decades of Bell test violations. Explanation 3. The measurement collapses a wave function that was never really undecided. That's just relabeling the mystery. If the explanation holds, then the past isn't finished until an observer, sometime later, finishes deciding what kind of question to ask it. Every photon that ever hit your retina may still be waiting on some future measurement to tell it what it was. The eraser proved the setup could be delayed. The next experiment proved distance doesn't save you either. Number 9. The Wheeler Delayed Choice Realization. Andrew Truscott's team at the Australian National University wasn't hunting for a philosophical bombshell. They were refining techniques to trap and manipulate single helium atoms with laser gratings, standard cold atom lab work. Standard quantum theory says an atom's path through a set of diffraction gratings is determined by whether the second grating is in place when the atom passes through. Wave behavior if it's there, particle behavior if it isn't. The stumble came when Truscott's team randomized whether the second grating existed only after the atom had already passed the point where, classically, it would have needed to decide. The atom's behavior matched a choice that hadn't been made yet. Truscott, Roman Kakamov, and colleagues published the result in Nature Physics in 2015, showing single atom interference consistent with Wheeler's 1978 thought experiment executed with matter instead of light. The failure parade, some argued the randomization wasn't happening late enough to rule out hidden signaling. Timing analysis closed that gap. Others proposed the atom's wave function was simply never localized to begin with, which is true, but doesn't explain why localization seems to depend on a future event. A third camp gave up trying to explain it locally and accepted non-local correlation as the price of admission. If this holds at atomic scale, there's no obvious reason it stops at yours. Every choice you've ever made may be less final than it felt. Small atoms bending under a choice made later is strange enough. The next case does it with objects big enough to sit on a chip. Number 8. Leggett-Garg Violations. Physicist Anthony Leggett wasn't trying to overturn causality either. He was trying to define, mathematically, the boundary between quantum and classical behavior in macroscopic systems, a question that had bothered him since the 1980s. The assumption baked into every classical description of the world is macrorealism. A system exists in one definite state at all times, and measuring it doesn't disturb what it would have been anyway. In 2010, Augustin Palacios-Laloy, François Mallet, Denis Villon, Patrice Bertet, and colleagues at the C in Saclay, France, tested this on a superconducting qubit, a circuit large enough to see under a microscope, not a subatomic particle. The Leggett-Garg inequality was violated. Published in Nature Physics in 2010, the experiment used weak, minimally disturbing measurements to show that the qubit's prior state could not be treated as fixed independent of how and when it was later measured. Explanation attempts, measurement disturbance alone, ruled out because the protocol was designed specifically to minimize it. Statistical artifact, checked and rejected across repeated trials. Classical hidden state models with retrocausal loopholes were proposed and then required assumptions stranger than the violation itself. If a circuit big enough to hold in your hand doesn't have a settled past before you look at it, the assumption that anything does starts to look like a convenient fiction. If a superconducting loop can leave its own past undecided, general relativity has already shown you what a truly open past could look like. Number 7. Closed time-like curves. Kurt Gödel wasn't working on time travel. In 1949, he was giving Albert Einstein a birthday gift, a rigorous solution to Einstein's own field equations, meant as a mathematical tribute from a close friend and colleague at Princeton's Institute for Advanced Study. The standard expectation in general relativity is that spacetime, however curved, still respects a consistent one-directional flow of time for any physical observer. Gödel's stumble, he found an exact solution describing a rotating universe in which an observer could, in principle, follow a path through spacetime that returned to their own past. Gödel published an example of a new type of cosmological solutions of Einstein's field equations of gravitation in Reviews of Modern Physics in 1949. Roy Kerr's 1963 solution for rotating black holes contains similar closed time-like curves inside the ring singularity. The failure parade, physicists pointed out our universe doesn't rotate the way Gödel's toy model requires, true, but beside the point, since the equations still permit it somewhere. Others invoked cosmic censorship to hide the pathological regions behind event horizons, plausible, but unproven. Stephen Hawking spent years developing the chronology protection conjecture specifically to explain why nature seems to forbid what its own laws allow. He never proved it. The equations that put a satellite in orbit and a GPS signal on your phone also, without any extra assumptions, permit a path back to yesterday. Nobody has shown why you can't take it. Gödel found the mathematics could permit a return trip. Your own brain, it turns out, is already rewriting the trip every time you remember it. Number 6. Memory reconsolidation. Kareem Nader wasn't trying to unsettle anyone about the nature of memory. As a postdoctoral researcher in Joseph Ledoux's lab at NU, he was investigating how fear memories are stored at the molecular level in rats. Standard neuroscience. The standard model of memory storage held that once a memory was consolidated into long-term storage, it was stable, writing it down, so to speak, finished the job permanently. The stumble, when Nader blocked protein synthesis in the amygdala immediately after a rat recalled a fear memory, the memory didn't just fail to strengthen, it vanished. As if recall had reopened the file and the interruption prevented it from being resaved. Nader, Glenn Schaff, and Joseph Ledoux published fear memories require protein synthesis in the amygdala for reconsolidation after retrieval in Nature in 2000. The failure parade, some argued this was retrieval-induced forgetting, a separate known phenomenon. But the protein synthesis dependence didn't match that mechanism. Others proposed the drug simply damaged unrelated brain function, controlled for and ruled out in follow-up studies across multiple labs. The consensus that emerged was worse than any single objection. Memory isn't replayed, it's rebuilt, and the version you experience each time is contingent on what happens during that specific act of recall. Every memory you've ever revisited is, chemically, a slightly different memory than the one before it. If recall itself is an edit, then someone who wanted to plant a memory wouldn't need your past at all, just your willingness to imagine it. Number 5. False memory implantation. Elizabeth Loftus wasn't trying to prove memory could be manufactured from nothing. In the early 1990s, she was studying the more modest question of how leading questions distort eyewitness testimony, work that had already made her a courtroom consultant. Standard assumption in both law and psychology at the time, a vivid, emotionally detailed memory, recounted with confidence, is more likely to be accurate. The stumble came in a study where Loftus and her student Jacqueline Pickrell gave subjects 4 childhood stories from a family member, 3 true, 1 entirely fabricated, describing the subject as lost in a shopping mall as a child. About a quarter of subjects came to believe the fabricated event had happened, and some added invented sensory detail on top of it. Loftus and Pickrell published The Formation of False Memories in Psychiatric Annals in 1995. The failure parade, critics argued the false memories were shallow or low confidence. Later studies with more elaborate suggestion techniques produced false memories subjects rated as more vivid than some of their real ones. Others hoped false memories would only stick to trivial events. Subsequent work implanted false memories of committing crimes, using similar methods. No reliable method has ever been found to distinguish, from the inside, a false memory from a true one. Somewhere in your own childhood, there may be a memory that never happened, sitting with exactly the same emotional weight as one that did, and you have no internal tool that can tell you which is which. If a human mind can be talked into inventing a past that never existed, the planet under your feet has been quietly doing something stranger, erasing chapters of its own. Number 4. Geological record gaps. Charles Walcott wasn't looking for missing time. In the late 19th century, as he mapped rock layers across the American West for the U.S. Geological Survey, he was doing routine stratigraphic cataloging. The standard expectation of the geological column is that layers of sediment accumulate in continuous order, each one a legible page of Earth's history stacked on the one before. Walcott and later generations of geologists kept running into the great unconformity. A surface where hundreds of millions of years of expected rock are simply absent, with ancient Precambrian basement rock sitting directly beneath much younger Cambrian layers. No transition in between. C. Brennan Keller and colleagues, including researchers at the Berkeley Geochronology Center, published a paper in the Proceedings of the National Academy of Sciences in 2019, arguing that a Neoproterozoic era glacial episode had scraped away roughly 3 to 5 vertical kilometers of crust in a single erosional event, consistent with a snowball Earth global glaciation. The failure parade, early explanations blamed simple regional erosion, too small in scale to account for a gap this consistent across continents. Others proposed the missing layers were never deposited at all. Isotopic evidence suggests they were, and were later removed. The glacial erosion model fits the data best, but doesn't fully explain why the timing lines up so precisely with the sudden explosion of complex animal life that follows it in the fossil record. Somewhere beneath your feet right now, there is very likely a gap in the record of the ground itself. A piece of the planet's memory physically removed, not lost, erased. The rock record has gaps where matter should be. The fossil record has a stranger problem, matter that shows up in the wrong place and time. Number 3. Fossil dating anomalies. Molecular biologists Mario Dos Reis, Philip Donahue, and Zhiheng Yang weren't trying to challenge the fossil record. Working across University College London and the University of Bristol, they were refining statistical methods to estimate species divergence times from DNA mutation rates, a well-established technique called the molecular clock. Standard practice assumes molecular clock estimates and fossil first appearance dates should converge on roughly the same timeline once calibrated properly. The stumble: when does Rice and colleagues applied rigorous Bayesian methods to placental mammal genomes, their molecular date for the group's origin came out tens of millions of years earlier than the oldest confirmed placental mammal fossil, implying an invisible ghost lineage evolving for millions of years with no physical trace. They published phylogenomic datasets provide both precision and accuracy in estimating the timescale of placental mammal phylogeny in Biology Letters in 2012. The failure parade, some argued the fossil record was simply incomplete near the Cretaceous-Paleogene boundary, plausible, but the size of the gap kept appearing across independent gene sets. Others suspected the molecular clock itself ran unevenly across lineages, corrected for, and the discrepancy persisted. Still, others proposed early mammals were too small and fragile to fossilize well, reasonable but unfalsifiable as a complete explanation. Entire branches of your own ancestry, by this evidence, existed and reproduced for millions of years while leaving absolutely nothing behind for anyone to ever find. An animal that leaves no fossil at all is unsettling. A patch of the sky that shouldn't exist at all is worse. Number 2. The CMB Cold Spot. The UMAP science team wasn't hunting for anomalies in 2004. They were producing what was meant to be a routine full-sky temperature map of the cosmic microwave background, the leftover radiation from 380,000 years after the Big Bang, to refine standard cosmological parameters. The standard model predicts small, statistically uniform temperature fluctuations across the entire sky, consistent with Gaussian random noise from early quantum fluctuations. Analyzing the data, Marcos Cruz and colleagues at the University of Cantabria in Spain identified a large, unusually cold, and statistically non-Gaussian region in the constellation Eridanus. Cruz and co-authors published the non-Gaussian cold spot in the UMAP data in monthly notices of the Royal Astronomical Society in 2005, and the region was later confirmed by the Planck satellite. In 2015, Istvan Sapudi and colleagues at the University of Hawaii published a paper in monthly notices of the Royal Astronomical Society linking the cold spot to a giant supervoid roughly 1.8 billion light-years across along the same line of sight. The failure parade, a simple foreground void, was proposed first. Shapudi's supervoid explains part of the effect, but not all of its depth and non-Gaussian statistics. A statistical fluke inside standard cosmology was proposed next. Its odds are estimated at less than 1 in a few hundred. The most persistent minority explanation involves a collision between our universe and another bubble universe in an eternally inflating multiverse, leaving a literal bruise in the oldest light we can see. Every photon of that light left its source before Earth existed, and it is still arriving cold in a way that current cosmology cannot fully close out. A hole in the birthlight of the universe is one kind of problem. What that light implies about the nature of now is another. Number 1. The block universe. Albert Einstein wasn't trying to dissolve the concept of the present moment. In developing special relativity in 1905, he was solving a technical problem in electrodynamics, reconciling Maxwell's equations with the constancy of the speed of light for all observers. Ordinary experience assumes there is one shared now that all observers agree on, with the past fixed, the future open, and the present a single universal line moving forward. The stumble was in the mathematics itself. Relativity showed that simultaneity is relative to an observer's motion, meaning two events one observer calls simultaneous, another observer moving relative to them will not. Philosophers C.W. Reitdijk in 1966 and Hilary Putnam in 1967, in a paper titled Time in Physical Geometry, published in the Journal of Philosophy, extended this formally. If simultaneity isn't absolute, then any event that is now for a distant observer moving relative to you is already, from their frame, part of your definite past or future. There is no way to draw a single consistent line across space-time that all observers agree separates has happened from, hasn't happened yet. The failure parade, some physicists argued this was a mathematical convenience with no ontological weight, but no experiment has ever found a preferred frame that would let now become absolute again. Others hoped quantum mechanics, with its apparent collapse of possibilities into a single outcome, would restore a privileged present. Decades of work on relativistic quantum field theory have not resolved the tension. What's left is a universe in which your birth, this exact sentence, and your death may already coexist as equally real. Fixed points on a four-dimensional structure that only feels like it's unfolding because your particular position inside it is moving through it one moment at a time. Nobody has found the physics that would tell you why now feels special, when nothing in the equation says it is. 10 separate fields. 10 separate teams, decades apart, none of them looking for this, and every one of them arrived at the same quiet, unresolved question, whether the past is really finished, or just the part of the block we happen to be facing away from. The universe has never once looked confused about any of this. It's the same as it's always been. We are the ones standing inside it, insisting there's a difference between what already happened and what hasn't happened yet, and unable, so far, to prove it. If you want to see more videos like this, click the video on screen now.